get into semantics. Now, you're probably going to look at me and say, well, we already talked about semantics. You're right. This is the first time, though, where we're actually going to merge a lot of different topics that we've already talked about. It's the first time that we're going to merge grammar, semantics, and syntax all together in a programming language. Now, what we have done so far individually is just not enough, and I'll show you a prime example of that here in a moment. So we're going to have to start combining all of those pieces together. Now, the good news is you've actually seen all of it, but separately. Now, with you seeing them all together, there's some hoops. I show you examples, and like I said, some of the examples are going to be kind of boring until we get to the exercises. So bear with me. There's also a couple different ways of doing the semantics as well as we're doing a parse tree, yes? You heard the word parse tree again. So again, all these pieces you've seen individually. Now we got to put them together because we need more control. The other part about semantics is program verification. All of you are so used to just programming on your laptop and expecting it to work and then think, I'm done. I know it pisses off a lot of you when you move to 221 and it doesn't matter who you have that, hey, it worked on my laptop but it didn't work in Unix. Get used to it. Because most of the time in your applications, they're not going to be just, number one, they're probably going to be platform independent, but number two, they're going to have to work on something else that you may not have started off with. Get used to it. I know it's a pain, but that's going to happen. Here's the other reason why. Do Macs work exactly the same way as a Windows machine? God, no. Does every individual... What was that? I didn't think so. Does every Windows machine work exactly the same way? No. Why? It has nothing to do about Windows. Doesn't have to really anything to do about Macs or any of that. Why? Why don't they work exactly the same? Why not? Why not? Yeah?
Different people have different stuff installed.
Different stuff installed, okay. What else? What else about two machines that could be different? Yeah, it's really the hardware. It's really the hardware, okay? Testing your hardware sounds like, well, it's debugging, or it's really about semantics that we have to make sure that it works. And if it doesn't, we need to add stuff to our semantics to make sure it works. This very simple idea has cost us lives, has cost us billions of dollars. I know you weren't born yet, but in the first Iraqi war, which is in the early 90s, we used something called the Patriot missile system. I'm sure you may have even heard about it. It's still used today. The bad part is that the system was used on different hardware. And when you're trying to shoot a missile down with this system, does 3 seconds matter if you're trying to shoot down a missile? You better believe it. What happened was, in the Patriot system, the clock on the CPU was slightly different than what the programmers expected. And as the computer and everything kept running, that distance between it, what it would actually do is fly the missile, look at it, and then guess where it would be in about 3 to 5 seconds. Okay? Bad part is that lag time grew longer. So it would search, not find anything, it wouldn't find a missile, even though the missile's farther down. It cost us lives, American lives. Because they either missed the missile or didn't fire the missile at all because of that lag time in the hardware. It's cost us lives, it's cost us money. Europe blew up a $7 billion satellite because, well, hardware. They really didn't check. Look up something for me real quick. On Google, that's fine. NASA. Do a general search on how long NASA tests its hardware before it shoots it up. It's going to be a while. Thank you, Google. My own phone started looking that up. Okay. Do a real quick search. How long does NASA test their hardware before they put it on it? Now, a missile used to be a shuttle. How long? If you see something, throw it back at me. Nobody yet?
They have a number, but not a time.
No, what is it?
15,000 tests.
Sorry about it.
15,000 tests.
Yeah, that's about right. Yeah, but does it say how long now? But no, that's about right.
This is about the Apollo program. It's
February to May? That seems a little short, actually. Okay.
The Ares 5
Oh, well, that's not NASA.
It says NASA.
Sorry, it's a different rocket. I'm actually looking at my notes here. The European one was Ariana. So no, I'm sorry, you're right. My bad. So let's put it this way. One came up with the number of tests. It was 15,000. We had another one that came up with about 4 months of testing. That's how long, actually, usually from when my experience being there, is longer than that. The neat part is NASA has a building for everything. They test the heat. They test how the heat works on the hardware. Because remember, if it's a satellite, it's going to be hot, then cold. Hot, then cold. What happens after you do that a lot? Yeah, it becomes brittle. Look at the roads in Texas. Okay, they're pretty brittle, aren't they? Okay, that's because hot, cold, and they eventually crack a little bit. Same thing happens to hardware. All these things they have to test before they go ahead and send things up. Now, it sounds like it's just hardware, but that's the important part. So we need to make sure that our software also incorporates any tests to make sure the hardware is up for it. So it's really, really important that we have that done. Put it that way. All right. So, by the way, there was even a chip issue. It was, I think it was an Intel Pentium chip. Couldn't even do math right in certain instances. Okay? Notice on your notes. There was a correct value, but there was what was getting back from the chip was obviously flawed. Now, you say it's 100th, 10 hundredths of a value, and then from there on out, it's pretty, so some of you are going to think, oh, that's not a big deal. Shoot something to Mars. Is a significant digit issue going to be a problem when you reach Mars or Saturn or Pluto? You better believe it. It's going to be a problem. So these are all things that you have to worry about with, well, software and hardware together. All right. So I'm skipping a page because I basically went over it. And yes, you're looking at parse trees again. Now, the interesting part about this is supposed to be the easy part of today, is drawing out the parse tree part. Yes, you're going to be drawing it out to match a certain syntax, but it's how we solve it on the bottom coming back up like we did last week to make sure that if we have an answer that it fits correctly. And that's our new addition to our attribute grammar, which I will go over here in a moment. But it's a look very similar to this. Now, did it highlight? Huh, okay. I thought I highlighted something and it didn't. I need you to highlight 2 words on this page. It's page 6. That is synthesized and inherited. You know what inherited means. It's passed down to the next value, children, node, whatever. You're not going to see inherited really today. You'll see that on Wednesday. But you'll see synthesized, and what synthesized means is that once we're done formulating the parse tree, we're going to actually have data that actually comes back up the tree in order to solve it. You've actually saw that every time we did an equation or something out of a tree. So that's really nothing new, but there's a term for it now. Now it's synthesized. And again, that's all the examples that you'll see. And again, that's information being passed up the tree. So, attribute grammars. What you see in front of you is not an attribute grammar. It's just a regular grammar that you've seen before. It looks more complicated only because, frankly, all the choices are on one line and the non-terminal symbols are a little bit longer in name. Other than that, there's nothing different. But here's the problem, is that what I'm trying to do with that grammar, and it's not going to work, is I'm trying to have an alphabet that has the same number of A's, same number of B's, same number of C's. See that N that's in between them. It says grammar 10 for A, B, C, and the ends between them. That's what I want. 3 A's, 3 B's, 3 C's. 4 A's, 4 B's, 4 C's, 50 A's, 50 B's, that. The bad part is that language, that grammar that we have right now, won't do it. It just can't. So that's the next page underneath, or next item underneath, is yeah, I can match it for what I want, but I also can screw it up. That's not what we want. We want to make sure that we have tighter controls on the grammar so that we can have exactly what we want. Right now, the way our grammars are just not enough. So we're going to add some other features to it. Okay. Now, I'm skipping the matching strings one. But I do want to go over, yeah, here we go. So we haven't seen the attribute grammar yet, at least the setup. But let me go over a couple of minor things when we get to it. You're going to see the arrow to the right. The arrow to the right is the same as you thought before. It's a meta symbol, basically saying, hey, this can be reduced to this part of the grammar. There is now a new symbol that goes the other way. That means assignment, which again, I'll show you in a minute, so bear with me. And then you have your syntax, your predicate, which is a true or false type of thing, and then your semantics, or exactly how is this supposed to be assigned a value. I need you to highlight that last line under semantics right here. Okay. Yeah, I'm going to go over steps here in a minute. Let me do this. So the example that I'm about to show you, and it's literally, why don't you scroll down one page so you can see the picture, which is this right here. Syntax portion of a grammar. Matter of fact, actually, I really want this. Let's go ahead and scroll down to that. And I got to go over the top part here. In the examples that I'm giving you, it's checking for, well, type. So what it really wants to do, all of you know this little error that you get. Let's say we try to do int I equals x, and x was a float. Now, can we get away with that in C++ of assigning a variable integer to an x that is a float? We can get away with it. Now, the compiler will hate you. It'll give you a warning, right? Okay. The other part is we could end up having some type of value difference. Let's say this was 2.6. What will my I value be? It'll be 2. So we could have some loss of value. And that's exactly what the compiler is going to tell you. Okay. Now, so that's the legit example we have. What this is trying to do is it's okay with integer equals integer plus integer. A real value equals a real plus integer. A real is okay with that, with another real plus real. Now, so that's the data checking that and data type checking that it wants. Because those three scenarios it's okay with. Now, let me show you one scenario that it's not okay with. And that is integer equals real plus int, or integer equals real plus real. It is not okay with those. Now, so think about it. It's kind of an example I just went over with the float. There would be some type of loss of memory, whereas the other one, real, is a little bit larger and can handle that. Okay? So no loss of data for the bottom three, loss of data in the top two. Everybody okay with that so far? Okay. Now, down to your grammar. I want you to, number one, I want you to just describe each part of the attribute grammar, which is the syntax rule, semantic rule, predicate, and there's one more, hang on. it that way. And can you describe what inheritance versus sentence size? Okay. I'm expecting you to get number one pretty well. You do that as a group. Number two sucks. And I haven't gone over all of it yet, but I want to see if you can at least try. Try to see if you can figure out that last part. Again, if you don't get that part, I'm not upset. You should be able to get number one. Let's put it that way. Okay? Go ahead and talk it over with the group. I haven't gone over it yet, but I bet you can figure out most of it. So go ahead and do number one and number two, and we'll huddle back up after that. Go over a couple of answers. So get to work. Okay. You should be able to do at least one and number four. You should be able to do one and four. Two and three, fine. I want you to at least try. Discuss it. You're wrong, so what? I don't care. I'm still going over to answer. Well, one and four, you should be able to get. All right, let's go over this. Now, I'm going to go over one, then four, and then I'm going to slowly answer two and three. I'm actually going to solve three or show you three first and then two. Okay? So my order is going to be totally off. So if you're taking notes, make sure you understand which one I'm tackling. So number one, from below, describe each part of the attribute grammar. Number one is the syntax rule. Somebody just describe what that is. Just again, none of this is meant to be hard. What's that? Yes, sir.
The syntax rule?
Yes, sir.
The syntax rule says that when you assign something, you set a variable with an expression.
Okay.
Assuming that they're the same type.
Okay, so we're assigning a value as long as the types are about the same. That's good. Using the grammar on the very, very top as well. That's part one of the syntax rule. What about the semantic rules? You actually did a little bit of semantics in your explanation, so be careful. What's a semantic rule? And what is it supposed to be doing? What is the semantic rules? So again, notice it's pretty well labeled. What is it doing in the grammar? In the attribute grammar? What's its only job? I appreciate it, but trust me, I'll pick another victim. Nobody, huh? Alright, then you need to write this down. This will be on your midterm. Your semantic rules is used for how assignment is done. In this example, it's the assignment of different data types. How do we use that to assign to different values or different values? Again, I showed you the chart that I had to get rid of. We had to check the data types to see if they were able to be meshed together. Remember, integer was actually the most restrictive. So that's what the semantic rules are doing this, or doing in this example. They're checking to see if the assignment types can be worked together in the equation. Alright, now let's see, predicate. The predicate portion, I think there was a couple, there was like rule 3 and 4. But notice, the predicate type, all it's doing is just checking to see if the two types are the same or close. So notice in number 2, it gives a little bit of leeway. As long as one's an int, the other's an int, if they're not the same, then they can do real. That's fine. Okay? But they at least had to have some type of actual type or expected type. Okay? Alright. Number 4, give me a very simple string that works with this grammar. Everything you need for the grammar is right in front of you. Notice the arrows that are going to the right. That's the same grammars that you worked with for weeks. It's just got a lot more crap to it now. Because again, we need tighter controls. So you should have an assignment that goes to a variable equals expression. Then the only expression that we're allowed is something plus another something. That's it. It's not a very big grammar for right now. And that's the reason is because I don't want to make it big. I want to make sure that we understand how the semantic rules are attached to a grammar to make sure that it works. Okay. Everybody okay with that? The third one. The third one's kind of interesting. Let me draw this one out. So if you know what the grammar is going to be,
Yeah.
let's see, we're going to have A equals B plus C. Does that sorry, hang on. There we go. Does that grammar work, does that syntax work with the grammar? A equals B plus C. It works. Okay. Now, here's the interesting part of this. If I were to draw a tree to this, my first symbol at the very top is going to be what? Not bar, by the way, it's what? Sign. Okay? Got a sign. And then a sign breaks down into what? Var equals expression. So var equals, I'm going to denote that it ends with a double, and expression. Okay, everybody okay with that? Okay, now I'm going to do expression. Expression equals what? Var plus var? Okay. Var plus var. Everybody okay with that? Okay. Now, the square braces 2 and 3 are actually basically position numbers. I know you and I instantly think of array numbers. I understand. Okay. But in reality, this is index number 2. Maybe it's a little thicker. This one over here will be index number 3. Now, is there an index 1 var? Yep. Right here. Okay. It's all about positioning. That's all it is in the equation. That's all it is. Nothing crazy. Thank you. Everybody okay with that? Okay. Now, so I'm scrolling down here. All right. Here's where things get interesting. Is that it goes over several data members within each node. So think of that picture that you have in front of you on your screens. Think of it basically having those nodes all have data members of actual type, expected type, and then it has a function called lookup to go ahead and grab the value or some other information for that node. Okay? That's what every one of those nodes have. So here's our first example of it actually at work. So notice, by the way, real equals real plus the integer. And remember, real in our example is more forgiving. Think of it as float. So A float equals A, another float plus B. Is that going to work out? Yeah. I'm sure, again, your compiler would complain something, but still, that should work out because, again, real is more fluid or more accepting. So in the tree, there's nothing crazy that what you're seeing in front of you. That's the same tree that I basically have up on your screens. But here's where things change. In order for us to do our data check or data type check, that's where things actually become, well, interesting. Is that we have to check each of the types to see if they'll work together on this. So on the way down, we get down to our original roots of A equals A plus B, but on the way back, called synthesis, we start double checking that the types can be used together when we are adding or assigning them to another variable. So that's the interesting part about it. So it's going to look like this. Now, what I need from you, and I'm going to switch this up here in a moment, with you and your laptops, I need you to look at the grammar that I gave you, a couple pages, actually I think the grammar is actually right below this too, if I'm not mistaken. Okay? I want you to look at the grammar, and I'm going to put the picture of the actual picture of the tree in front of you here as soon as I get this right. All right. So again, you should be looking at the grammar below this picture. But what's happening is from the bottom, we're at the bottom now, we've checked that the syntax works. Now from the bottom, we're going to check, okay, well, this one's a real type, that's okay. This one's an integer type, that's okay. Once I merge the two together, can I get away with it? And that's where you should be looking at rule number 2, because that's your first time where you have your addition of your two variables. Does the condition allow us to have an integer and a real work together? The answer is yes. So as long as it's okay there, we can move up to our next step, which is after that we look at our assignments. I should really do that in another color. And now we have an assignment with our expression and check to see if we can get away with it that way. And we should be able to as well. What's up?
I can't see what you're writing.
Oh, my bad. Think about it. Oh, I put it on the copy. Jeez. Yeah, thank you. Sorry about that. Move this over here. And there we go. Thank you. Had a copy of it, didn't I? So notice how as we start progressing up the tree, we're checking the semantic rules to see if we can get away with the data members of each of the nodes, which are the data types. Everybody okay with that, though? Is there any questions on that? This is a good time to ask. Yes, sir?
So the if statement was part of the grammar?
Yes, sir. Yeah, that if statement is literally part of it. And all it's doing is checking the actual type. I forget which one it is. Expected type or actual type. I'll have to double check that.
Actual type.
It's the actual type, perfect. It's checking to see if those two can match. Now remember, in most cases it'll work just fine, but there is one for integers. If they're both ints, it has to be an int.
Yeah.
Otherwise, any other option, then it's a real. And that's a big difference because remember, real is more flexible than an integer. Okay? But then at the very end, I got to check rule 1 when I sign it. I basically got to say, hey, is the other side an integer? So if that left side's an integer, everything has to be an integer from the right-hand side. Otherwise, it'll not like you. You know, it sounds like a compiler.
Where do you check that?
Right? What's that?
Where do you check
You
it?
check that in rule number 1, right where it says the expected type, and then go from there. Okay. All right. So let's find one that doesn't work. The one that doesn't work, and again, I'm using a copy here, is this one. Okay, give me 1 second here. And do this one. All right. Now on this one, the only thing that is different about the syntax is that on the left-hand side, A is an integer, and I'm saying left-hand side, the equal sign. Make sure it's clarified. Okay, clear. So as you know, because I just went over the different scenarios, it's not going to like this because B is a real number, meaning it could have significant digits. So there's going to be some data loss. It's not going to like this. And hopefully you understand the theory of why. But it's still going to do the same process. It's still going to go up the tree, starting from the bottom once everything's created, check. It's still okay with rule number 2, which is right here. But as soon as we get to rule number 1, it doesn't like it because, again, integer is much more stringent than having a real, which would be on the other side of the equal sign. Now, here's the good news. The semantics of this grammar, it's not always about data type check. Some of it is about actually how things are calculated in order to kind of help out the progression. And that's what I'm going to show you here in a moment. So it doesn't always have to be that way, but it is set up very simple. Put it that way. All right, so let me scroll down. Oops. what that button was. All right. So here's another example for you. And again, this one is an exercise that you're about to start with. Number 2, it doesn't have anything to do with type checking, so I'm sure some of you will be happy about that. But it has some, at least, great applications for it. So by the way, you'll use this for your next exercise. So wake up a little bit for me here. It's only 3 minutes, so that's good news.
Our synthesis attribute grammar example. A couple of interesting things to set up here. First of all is the actual grammar itself. Notice I do have semantic rules for both rules, number 1 and number 2. Number 1 handles a number, and it further breaks down into a number, a digit, or digit itself, and digits is literally just the values themselves, 1, 2 to 9. The important part is the rules themselves, which I will go over here in a little bit, but the easiest one so far is going to be the digit at the end, where we just grab the digit value and set it to the number value. The first step is the first one, find out the target syntax, and that's going to be 4, 2, 3. Second step is going to be laying out the parse tree, which I'm going to do right now. So here's what the parse tree looks like. Very, very simple. Starting out with number, because I need 3 different numbers, I needed to use the first portion here, number and digit, to break it down a couple times to get all 3 of my digits. Now you'll notice that the digits already have a value of 4, 2, and 3, and we'll need to use that. Now in synthesis, notice that our answer at the end will be calculated at the top very nodes, and that's synthesis starting from the bottom to get our values going up to get our final answer. In our first node, starting from the bottom most here, I'm actually going to use rule number 2 here, the semantic rule for number 2, and that is that num.val equals digit.val. Well, it's only connected. Here's num, and then it translates into digit, so that 4 is going to move up into num. And the other interesting part is that's the only time I'm ever going to use rule number 2, because this node here needs num and a digit, which this one doesn't work for. This one again needs the same exact thing. So we'll move on here in a sec. So now num gets that value of 4. Moving on, this num has 2 items that it relies on. It needs the value from number, and then this value of digit over here, which using what we have here for num, and digit, we have semantic rule of, now notice the equal sign, so we do the right hand side first. We have num2, which is going to be our lowest one, dot value times 10 plus the digit dot value. So we're going to multiply 4 times 10 and add it to the 2, so you should get a 42 at the end. So that's what's happening on this one. And we do exactly the same thing for the one up here, where again, it requires 2 different attributes, not attributes, but 2 different nodes here of num and digit. So it's exactly the same syntax rule number 1, and we need that semantic rule. Using rule number 1, we'll have 42 times 10 this time instead of just 4, plus 3, which our final answer does end up being 423.
So notice how the overall progression of this was done. First, you built the parse tree. You made sure that the syntax worked with the grammar. Number 2 is then you use that parse tree to basically figure out as your synthesis starts to work up, because again, we're not worried about inheritance yet. That'll be on Wednesday. However, in this case, the semantic rule is used for basically the tree solving itself on the bottom on up. So you notice the semantic rules are not really doing anything about type checking or anything of that nature. It's actually calculating the value for this, which is a help. Let's put it that way. Right? So after that, one other thing I wanted to demonstrate here, not really demonstrate, but point out though, is that
now please note that I started from the bottom up. I used all the current rules.
I can't do it on this because otherwise it'll play. But notice I was trying to show you that basically you're matching the grammar with the part of the tree from bottom up. So that's why I used rule 2 first, because you just have num connected to digit. That was your semantics rule or syntax rule number 2, which is digit, and then you move up from there using the other rules. So, I know we only have about 4 minutes left, gang, so we double check me?
Yeah.
Okay. So this is what we'll start off on Wednesday. Is that I'm not giving you any, well, I'm giving you a lot in just the pictures that you see in front of you. You're going to give me the grammar, you're going to give me the semantics of it, and you're going to prove that it works. It's hard to believe, but the only thing I really needed to give you is straight in front of you. And you should be able to figure all that out. Now again, this semantics is going to be used for calculation. You're converting from binary to decimal. So it's nothing about semantics check, or data type check or anything else like that. It's about calculating. It's going to look similar to what I just showed you in the exercise. Yeah, a little bit. But that's about it. There's actually a lot of differences. Okay? So that's what we're going to start off with on Wednesday, and we'll go over answers, all that good stuff. Last part before I let you loose is every node, just like we're using linked lists or something in data structures, every node can have data members, meaning it could be a value, could be total, could be expected type, could be really anything. In order for you to double check and make sure that this works, you're free to add information to it in order for it to work. That's what's going to make your answer very different than maybe the person beside you or the team beside you on getting it solved. You also got to watch you not use an inheritance. And some of you will do that by accident. That's okay. It doesn't bother me. All right, to Wednesday. I will see you guys out.